So now I'm going to walk you guys through excuse me, what I did for the laminar model, which I can rename here. This is the laminar, this is the turbulent, and this is the inviscid. So I kept the geometry and the mesh the same. The only thing that I changed for all of these, as you can see, is the setup and below. So I'm going to go ahead and open this file in double position for the viscous laminar model. And once this open, we're going to see here that I chose a different method for this one. Like for the first inviscid model, we used the simple method with the presto pressure. Once this opens up, we're going to see here that we used a coupled method with a second order pressure. So, okay, now that this is finishing up loading, we're going to see here we changed the model to viscous laminar, which is good. Our materials, well, now we have to input a viscosity, because since it's no longer inviscid, we're going to have viscosity here. And I try to keep the Reynolds number as low as possible while still maintaining some believable data points. Not data points, like data in general. So I made the density very, very low, which is pretty low for air, and the viscosity pretty high for air, to try to get that Reynolds number down, which I got it down to about 400. The boundary conditions, I made the inlet, again trying to lower the Reynolds number, made it 0.1 meters per second, and the outlet remained as a pressure outlet with no reverse flow. Our reference values were computed from the inlet, which changed our density here, and our velocity values, and the viscosity, which is everything we input before. And the method, which is what I was referring to earlier, we no longer use the simple one for inviscid, but the coupled one. Excuse me. And we changed this here, the spatial discretization, to second order. And once that was done, we turned down the residuals like I said I would for our actual runs, which is what I'm showing you guys now, which is a very small convergence criteria. And after we initialize this, we can go ahead and run our calculation, which I increased the number of iterations as well. So once we run this, we can go ahead and, well, let me initialize this first. And once we run this, we're going to be able to see everything that it will output. So I'm going to run this and I'll get back to you guys. So now that our calculation is complete, we can go ahead and pull the things that we want out of it. We can go ahead and grab the static pressure on the wall. On everything, I should say, and see here what it looks like. We can do the same for our velocity, selecting everything, and you can see here that it has this sort of wake region, and we can go to our XY plot and pull the pressure coefficient on the cylinder wall, which starts at 1 and looks pretty good for our laminar, which makes this separation here make sense because of our wake region. You know, it's not perfectly symmetric. And we can go down to our forces on the cylinder wall and it should be somewhere near 1.2. It's not there, but this number should be higher than the turbulent flow coefficient of drag, which we will prove now that it is. So now that we have that, we can go ahead and look at our streamlines. So we're going to open up our results here and check out the streamlines that we have gotten. We should already have a streamline set up. Yep, there we go. So if I open this here, we can raise this number to go ahead and refine this wake region that we're getting here in the back. So we pan, see closer, we can see what our streamlines look like. And that's it for our laminar flow.